Now, exercise of chapter 1. Example 1.1. What is the force between two small charged spheres having charges of 2 into 10 raised to minus 7 coulomb and 3 into 10 raised to minus 7 coulomb, placed 30 centimeter apart in air? Now see, Q1 given to you, 2 into 10 raised to minus 7 coulomb, Q2 that is 3 into 10 raised to minus 7 coulomb. Separation that is 30 centimeter means 0.3 meter. Now as per Coulomb's law, the force between two charges F equal to K Q1 Q2 upon R square. Substitute K equal to 9 into 10 raised to 9, Q1 2 into 10 raised to minus 7, Q2 3 into 10 raised to minus 7 upon R 0.3 and square of it. Solve this one, you will get the force. Now here both the given charges are positive charges, and we know this thing, like charges repel each other, so this particular force will be repulsive one. Clear? Now example 1.2. The electrostatic force on a small sphere of charge 0.4 microcoulomb due to another small sphere of charge minus 0.8 microcoulomb in air is 0.2 Newton. A. What is the distance between the two spheres? B. What is the force on the second sphere due to the first one? Now charge Q1 given to you, that is 0.4 microcoulomb. So that is 4 into 10 raised to minus 7 coulomb. Q2 minus 0.8 microcoulomb. So minus 8 into 10 raised to minus 7 coulomb. Okay. F that is equal to 0.2 Newton. And what is the separation between these two that we want to find? Here magnitude of the force as per Coulomb's law, that is K Q1 Q2 upon R square. So R square equal to K Q1 Q2 by F. So R that is equal to K Q1 Q2 by F whole raised to 1 by 2. Now substitute the values. K 9 into 10 raised to 9, Q1 4 into 10 raised to minus 7, Q2 8 into 10 raised to minus 7 upon 2 into 10 raised to minus 1, that is the force. And now solve this one and then take square root of it, you will get the separation between those two. Now here these two charges given to you are opposite charges. One is positive, another one is negative. So this particular force that will be attractive one. Now second question, that is what is the force on second sphere due to the first one? That will be the same one, because this is the force between those two charges. So we can say that is force on 1 by 2 or force on 2 by 1. It is one of the same thing. So clear to all of you? Example 1.3. Check that the ratio Ke square upon Gmemp is dimensionless. Look up a table of physical constants and determine the value of this ratio and what does the ratio signify. So first, unit of Ke square upon Gmemp. So unit of K, that is Newton meter square per Coulomb square. For E square, that is Coulomb square. Unit of G, that is Newton meter square per kilogram square. Then mass of electron, mass of proton. So units are kilogram, kilogram. So Newton cancelled, meter square cancelled. This Coulomb raised to minus 2 and Coulomb square cancelled. Kilogram raised to minus 2 and kilogram cancelled. Means this ratio, that is unitless. Unitless means it is dimensionless. So dimensions of Ke square upon Gmemp, that will be M0, L0, T0. Okay. Now, if we substitute all the values here for K, 9 into 10 raised to 9. For E, 1.6 into 10 raised to minus 19. For G, 6.67 into 10 raised to minus 11. Then mass of electron 9.1 into 10 raised to minus 31. And mass of proton, that is 1.66 into 10 raised to minus 27 kilogram. And then after, if we solve it, then we will get resultant answer, that is 2.4 into 10 raised to 39. So here, for the given separation between two charges, or we can say charged particles, the ratio of electric force to gravitational force, that is of the order of 10 raised to 39, it implies that electric force, that is tremendous large compared to gravitational force. Clear to all of you? Example 1.4. A. Explain the meaning of the statement electric charge of the body is quantized. It implies that in nature, the charge available, that is always in the integer multiple of some fundamental charge. And experimentally, we can observe this thing. The charge available in the nature, that is always in the integer multiple of charge of electron, or we can say proton. Magnitude wise, it is 1.6 into 10 raised to minus 19, and it is represented by small e. So charge available in the nature, that is n into e, where n, that is the integer. Okay, and this particular fact observed in the nature, that is known as electric charge of the body is quantized. In the nature, charge is not available like 0.5 into E or 1.5 into E, not like that. So this particular fact is called quantization of electric charge, or we can say electric charge of the body is quantized. Now question B. Why can one ignore quantization of electric charge when dealing with macroscopic? It implies large scale charges. Suppose we consider 1 microcoulomb charge. Then 1 microcoulomb charge, that is 10 raised to minus 6 coulomb. Now if we take 1 microcoulomb charge, that is equal to Ne. So N, that is equal to 10 raised to minus 6 upon 1.6 into 10 raised to minus 19. So when you solve this one, your answer, that will be 0.625 into 10 raised to 3. Clear? But now see here, we can say this thing, 1 microcoulomb charge, that is this much times larger than charge E. And this is tremendous large one. So at this particular scale, one can ignore this fact. Clear? Now example 1.5. When a glass rod is rubbed with a silk cloth, charges appears on both. A similar phenomenon is observed with many other pairs of bodies. Explain how this observation is consistent with the law of conservation of charge. See, law of conservation of charge suggests this thing: charge neither be created nor be destroyed. It can be transferred from one body to another body. So here, when glass rod is rubbed with a silk cloth, at that time, glass rod becomes positively charged and silk cloth becomes negatively charged. Due to transfer of negatively charged particles, electrons from glass rod to silk cloth. But here, the amount of positive charge deposited on glass rod and amount of negative charge deposited on silk cloth, that will be same one. And due to that, before the process and after the process, net charge, that remains same one. And this particular fact, that is conservation of charge. Okay, so this phenomenon that is inconsistent with the law of conservation of charge. Clear to all of you? Now example 1.6. 4-point charges QA equal to 2 microcoulomb, QB equal to minus 5 microcoulomb, QC equal to 2 microcoulomb and QD equal to minus 5 microcoulomb are located at the corners of a square ABCD of side 10 centimeter. What is the force on charge of 1 microcoulomb placed at the center of the square? Now see, suppose we represent all these charges at the corners of a square, then we can observe this thing. These diagonally opposite charges are identical. So here at A 2 microcoulomb, at C 2 microcoulomb. It implies that if at the center of these two charges any charge is placed, then the net force that will be 0. Similarly, at B and D also the identical charges and 1 microcoulomb that will be at the center of the line joining to this B and D because are diagonally opposite. So again the net force on charge 1 microcoulomb that will be 0. So resultantly we can say the net force on 1 microcoulomb charge that will be 0. Clear to all of you? Now example 1.7. An electrostatic field line is a continuous curve. That is, a field line cannot have sudden breaks. Why not? See, field lines always start from positive charge and end up at negative charge. If there is a sudden break in this line, then see, actually field line suggests this thing: when a charge is allowed to move, then it will experience the force in such a way that its path will be on this field line. So if there is a sudden break, then their charge have to jump from one side to another side. But we never observe such things experimentally. So we can say there will be no sudden break in the field line. Then B, explain why two field lines never cross each other at any point. Now see, tangent drawn at any point on the electric field line give you the direction of electric field at that particular point. Now, if two field lines intersect each other, then at the point of intersection, two tangent can be drawn. It implies that at the point of intersection, two directions of electric field will be obtained, which is never possible because any vector have only one direction at any point. Clear? So if at that particular point of intersection two directions of electric fields are there, means if any charge is placed there, then it will experience the force in two directions, which is never possible. So two field lines never intersect each other, or it is impossible to intersect each other. Clear? Now example 1.8. 2-point charges QA equal to 3 microcoulomb and QB equal to minus 3 microcoulomb are located 20 centimeter apart in vacuum. A. What is the electric field at the midpoint O on the line joining AB, the two charges? B. If a negative test charge of magnitude 1.5 into 10 raised to minus 9 coulomb is placed at this point, then what is the force experienced by the test charge? Now suppose as shown in the figure, we have two charges QA and QB separated by 20 centimeter. Now, this one is the line joining to these two charges. At the center, O, we want to find the electric field. Now, first electric field due to charge QA, that is EA equal to KQA upon R square as per the equation of the electric field due to a point charge. Substitute K equal to 9 into 10 raised to 9, QA 3 into 10 raised to minus 6 coulomb. Separation, so QA to midpoint, that is 10 centimeter, so it is 10 raised to minus 1 meter, and square of it give you 10 raised to minus 2. When you solve this one, you will get 27 into 10 raised to 5 Newton per coulomb. Magnitude wise, electric field due to charge QB, that will be also same one, because magnitude wise charge QB and charge QA are same one, and this point O, that is also at the same distance from the QA and QB. But here, if we think about the direction of electric field, then due to QA is positive charge. So electric field that is in outward direction, that is in the direction from O to QB. Now charge QB is negative. So due to that, the electric field is towards the charge. So due to QB also, the electric field is in the direction O to QB. It implies that both the fields are in the same direction O to QB. So resultant electric field at O, that is E equal to EA plus EB, but EA and EB both are same one. So we can write 2 times 27 into 10 raised to 5, and we will get the resultant electric field 54 into 10 raised to 5 Newton per coulomb. Clear? Now, a negative charge Q equal to 1.5 into 10 raised to minus 9 coulomb is placed at this point. Then the force on it, that is Q into E, that is 1.5 into 10 raised to minus 9 into 54 into 10 raised to 5. You will get the answer. And the direction of this force when the charge is negative, so direction of the force, that is in the opposite direction of net electric field. So direction of this force, that will be from O to QA. Clear? Now next example, 1.9. A system has two charges, QA equal to 2.5 into 10 raised to minus 7 coulomb and QB equal to minus 2.5 into 10 raised to minus 7 coulomb. Located at points A, 0, 0, minus 15 centimeter and B, 0, 0, plus 15 centimeter respectively. What are the total charge and electric dipole moment of the system? Say here given charges are equal in magnitude but are opposite and separated by some finite distance. So this is the dipole. Okay. Now QA, that is 2.5 into 10 raised to minus 7 coulomb. QB, that is minus 2.5 into 10 raised to minus 7 coulomb. Separation between these two, that is minus 15 to plus 15 means 30 centimeter, that is 0.3 meter. So net charge of the system, that is the algebraic summation of all the charges of the system. So capital Q, that is QA plus QB. So that will be equal to 0. Okay. Then the dipole moment P, that is Q into 2A. So Q, substitute the value 2.5 into 10 raised to minus 7 into 0.3, then solve it, your answer, this much coulomb into meter. Clear? Now example 1.10. An electric dipole with dipole moment 4 into 10 raised to minus 9 coulomb meter is aligned at 30 degree with the direction of a uniform electric field of magnitude 5 into 10 raised to 4 Newton per coulomb. Calculate the magnitude of the torque acting on the dipole. Now dipole moment given to you, that is 4 into 10 raised to minus 9 coulomb meter. Electric field, that is 5 into 10 raised to 4 Newton per coulomb, and it is aligned at an angle theta equal to 30 degree. Now torque acting on the dipole when it is placed in the uniform electric field, that is given by tau equal to Pe sine theta. Substitute P equal to 4 into 10 raised to minus 9, E equal to 5 into 10 raised to 4, theta 30, so sine 30, then solve it, you will get the torque this much Newton into meter. Clear?